And now, for example, for this accepted, I need to provide, since this is a Bayes network, I have to provide the probability that paper.accepted is true given paper.quality and paper.review.mood. That's what I'm asking you to give. Okay? So, I may give you this. This may be the number. So, either I would have given you, as part of giving the relational Bayes network, I need to give you the skeleton, which is the topology, which is like equivalent of topology in the normal case. Except now the topology is our templates of equivalence classes. And it sort of grows. Okay, here's a sanity check. So if I get more authors, the underlying Bayes network is increasing in size. Have you in this class seen a situation where the underlying Bayes network keeps increasing in size? Where? When? What?
When you have the parameters
in Bayes learning. Okay, right? And that's exactly true. Okay, so in some sense, in Bayes learning, in fact, there is a very interesting connection between what you are doing here, which is sort of thinking in terms of predicate, logic, etc., and what you wound up doing in Bayes learning. Basically, because these structured models, one type of structured model is a plate model. And when you have a Bayes network, you have the parameters affecting the plate corresponding to the data. And as more data points come, you keep copying the plate. You did the same thing there. In fact, once the parameter is decided, how it affects the data point, that CPT is constant. As new data points come, they just have more places in the network, but they use the same exact CPTs from the theta. Do you see what I'm saying? So in some sense, you saw a relational version of the Bayes network. Plate models are essentially relational versions too. Okay, but anyway, you're looking at this here. So I gave you the skeleton, which is the objects, their attributes, the interconnections. Who is dependent on who. And then I also have to give the CPTs. The CPT in this particular case is, this one. Now to specify it, I have to give this. To learn it, you have to learn it. Now as I said, as the number of authors, papers, reviews increase, this corresponds to a much bigger Bayes network. But it has very few free parameters. So the complexity measure for a RBN is lower if you look at the structure learning. So given the same data, if you learn a relational Bayes network, you have a lower complexity than if you learn a non-relational Bayes network, because then you are assuming everybody is created completely different. Everybody is unique. Okay? So once you have a relational skeleton, now if you have two authors, this is what I've been saying. If I have two authors, this guy wrote 2 papers, this guy wrote 1 paper, this guy has 2 reviewers, this guy has 1 review, and so you basically throw in all of them, but you know how to write the full Bayes network. Writing a full Bayes network starting from the relational skeleton is like starting from a predicate logic database and propositionalizing it. Right? If I know the finite domains, if you don't have functions, which is what would make things first order and you screen. If you only have finite domains for the variables, right? Then essentially given a predicate logic database, you can write an exponentially larger but not infinite propositional database. Okay, and the same thing here. So I have a relational network, I can write a underlying Bayes network. The thing is, there's a humongous similarity in the CPTs being used. The CPT here is the same as the CPT here is the same as the CPT here. And that reduces the number of data points, number of parameters you need to know. Okay? So PRMs versus Bayes nets, the semantics of PRMs are really in terms of the underlying Bayes nets. Just as you can give semantics for predicate logic in terms of the underlying propositional database. Okay, that doesn't work very well in first order case because that's where you needed like Herbrand semantic, Herbrand universe and all that fun stuff. Okay. Otherwise, you can get semantics of the predicate logic completely in terms of the assembly language, which is your propositional logic. Okay. So for here, the Bayes network would be the assembly language for the relational Bayes networks. Okay. However, the PRM defines the dependencies at the class level rather than at the object level. That means these dependencies and their CPTs are used for all objects of that class. And then the PRM also allows dependencies between the attributes of different objects. That means the reviewer's mood affects the paper's decision. That's allowed. Okay. One interesting, I already sort of told you the learning is easy. I will do some more discussion of this when I come back next class, but I want you to understand what's interesting about relational Bayes networks and how it's kind of connected to something that I told you about lifted planning many classes back. Okay. So you have a skeleton like this and you want to do inference, let's say. What can you do? You can convert the skeleton, given the number of objects, you can compile it down into a big Bayes network. Then I say I have a Bayes network, I know how to do inference. So I have reduced it to a problem I know. The same thing is true for relational reasoning versus relational logic reasoning versus propositional logic reasoning. You can always say you can do relational logic reasoning by just converting it to an equivalent propositional database and do inference there. Okay? But oftentimes that could be very, very inefficient. Because, think about it this way, right? Suppose I have a big database of 10,000, predicate, let's just say 100 predicate logic sentences, and, with finite quantification, for all x, for all x, rich x means happy x. And then I have a rich Tom, and I want to see whether happy Tom is true. Okay, if the way you're going to do this is directly converting this whole thing into a predicate logic, propositional logic database, and then do inference, then you wasted a humongous amount of time, because your compilation, basically looked at everything that's unconnected to the inference at hand. Whereas you could actually directly do lifted inference. You can actually see that for all x, rich x implies happy x, rich Tom, x and Tom can be unified. Unification is lifting, by the way. Okay? And so rich Tom, happy Tom can be derived. That is sticking to the relational level, predicate level, and doing more efficient inference. That's what is called lifting. And in between lifting and full compilation is a different idea, which is you say, okay, you are interested only in richness of Tom, and you have 100 sentences, but I think only these 2 sentences have anything to do with richness of Tom. So I will only convert them into propositional logic, then do propositional logic inference on them. That would be an in-between idea. Okay, so the in-between idea is, rather than generate the entire Bayes network assembly language, which is Bayes network for us is propositional logic for logic, you would only generate a piece of the Bayes network. That's actually, and you have to prove to yourself that the stuff that you did not generate won't affect the probabilities that you're trying to compute. If it's hard in logic, it's somewhat harder in probability, because more things affect each other. At least in logic, in the entailment case, you don't have abractive entailment. Evidence does not change the status of the cause. But in probabilistic case, evidence changes the likelihood of the cause. So it's less likely. So you will have you have fewer opportunities to say this is not relevant, this is not relevant. But there are still some opportunities. And the more effective algorithms for doing inference in relational models essentially either do lifted inference or reduce the compilation to only the part of the overall network that is really relevant for answering that query. And once they do that, so instead of getting this big a thing, suppose I just use this much, then I just use my normal Bayes network inference. Okay, now it sort of looks like cheating, right? Because I said, wow, there is something called predicate logic, but then the first thing you do is convert it into propositional logic. It's more or less what I'm saying. So if you don't really do lifted inference, you would not have believed predicate logic is a topic on its own. And the reason you still need to believe it's a topic on its own is because predicate logic is making assumptions about regularity in the world. How you reason with it is different from what assumptions you make about the regularity of the world. Okay? So in RBNs, in relational networks, there is a lot of work that's going on in how to do inference more efficiently at the lifted level, or by just looking at the piece of the base network that matters. And learning, which is the last slide, and actually I can be done today. I might come back next week and we'll do just general discussion. Learning is easy, because as I said, if you'll again have complete data case, hidden data case, structured learning case. But if you just want to understand the complete data case, essentially you have lots of data, but all of them, there's a big base network, but all of them have the same parameters. Large pieces of the base network is copying the same parameters. So in essence, the same amount of data goes a longer way for a relational base network because it is learning fewer parameters. And you do the learning itself the same exact way, the counts. Okay? So there is nothing to teach about learning in relational base networks. It's actually easier. At least for the complete data case. Inference is a different matter. Inference, if you don't mind just converting it into the underlying base network, you don't need to teach that either. If not, you can talk about how do you look for the relevant parts of the base network on which to do the reasoning. Okay, and there's a lot of work on how to do that more effectively. That's been going on. But irrespective of whether you do inference this way or in a more efficient way, learning wise, for at least the complete data case, because for complete data case in base networks you never have to do inference as part of learning. You should use MLE. This is stuff that should become second nature to you after the SLN, statistical learning lectures. Okay, if you're doing complete data and you're using MLE, then as part of learning you don't need to do inference. If you have incomplete data, then you need to do inference. If you're doing base learning, then you need to do inference because there's no learning. In fact, you just compute the posterior. So you can do learning on these networks without knowing how to do inference on them. And it could very well be that predicate logic is just syntactic sugar. In fact, logicians believe that predicate logic is syntactic sugar. It's only at the first order level that logic's expressiveness changes. That brings up the question of how do I generalize this into first order. Read the chapter. There's a small section in base, Russell stuff. But that's basically unknown objects, etc. Okay. So we'll do a little more probably on this when I come back next class. But I'll send you the paper that I was basing my discussion on. And come to next class prepared to do general discussion on anything that we have covered in this entire semester. Okay. Thank you.